A kaleidoscope isn't a toy. It's a device of precision optics, governed by rigid laws of physics. What if you could alter those laws? High-end designs let you change the mirror angle, bending reality. Some even defy flat geometry, using tapered mirrors to create the illusion of a 3D sphere. These effects all stem from one fundamental idea. The mirror angle determines everything you see. We'll decode the math, examine radical mirror systems, and reveal the science of optical art. The secret begins with a formula. 360 degrees divided by the angle equals the pattern's slices. For a perfect pattern with no gaps, that angle must be an exact sub-multiple of 360. Precision is required. While math suggests infinite images, physics dictates a light loss with each reflection, causing a gentle fade. This union of math and physics was first mastered by Sir David Brewster, who patented it in 1817 as a scientific tool. So, we have the rule. Angle dictates symmetry. But how is this rule applied? It starts with the number of mirrors. Yet Brewster's genius wasn't just the basics. He foresaw many advanced features. What were these modern ideas? A two-mirror system forms a V shape. This isolates reflections, creating a single mandala floating in a black void. Adding a third mirror closes the system. Reflections bounce off all surfaces, creating a continuous quilt of patterns. A 60-60-60 triangle fills the view with triangles. A 45 to 45 to 90 triangle makes a rectangular grid-like pattern. Great geometry needs great mirrors. High-end scopes use first surface mirrors, stopping the ghost reflections. This quest for perfection extends to assembly. The slightest misalignment can distort the entire pattern, ruining the effect. So, we have the core systems and quality parts. But how do artists bend these rules to produce something new? Recall Brewster's foresight? Here is his idea made real. The polyangular system. The angle is physically adjustable. Another variation is the tapered system. Non-parallel mirrors form a cone, tricking the brain into seeing a 3D sphere. And who says it must be a triangle? Four mirror systems generate square patterns. Cylindrical tubes make spiral effects. The most radical design is the Kaleidoscope. A lens at the end turns anything you view into a kaleidoscopic image. The mirror system defines the canvas. But the paint, the objects being reflected, is its own separate art form. The object cell at the end is vital. High-end versions are liquid-filled, allowing tiny crystals to drift gracefully. Artists add nuance here, placing a colorless textured plate before the colored bits to soften colors or add a ghost pattern. This deep interplay of math and art wasn't confined to the tube. Its influence appeared in a different, larger art form. But what? First, why do these patterns feel so perfect? The simple math is a door to a deeper field. Reflection-generated groups. What this advanced geometry guarantees is that the image isn't just pretty. It's a visually flawless slice of infinity. That idea of perfect repeating geometry had a huge impact. The art form it inspired? American quilt making. The mathematical principles set by Brewster weren't just for optics. They became aesthetic rules for fabric artists. Just as a three-mirror system creates a quilt of patterns, quilters adopted this vision of a completely filled canvas. From Brewster's lab to the quilter's table, the core principles proved their power. Where does this progression lead now? Today, these ideas live on in new forms: computer-generated art, digital camera integrations, and massive architectural installations. Whether a 19th-century device or a digital projection, the magic comes from one place: the precise angle between mirrors. That angle dictates the symmetry. The quality of the materials and the objects inside just determine how clearly that beauty is shown. A kaleidoscope proves that a single angle can contain an ordered, infinite, and beautiful universe. What other objects hide such artistry?